CLI and a cross-platform IDE for C and C++. Download now.
My name is Robert Schimkowitsch. I work on control center systems for hydroelectric power plants with 25 years of experience, approximately 15 of that with C++ and Qt, mostly in the desktop and UI space. Nowadays, I also do refinement of requirements, a little architecture, discussing code design, and generally trying to make my junior members of the team more productive. I love working with other people, which is why I also co-founded the C++ user group Vienna. So if you're ever around there, come join us at one of our events, no matter whether you want to watch a talk or give a talk or just have a drink with us. Over the course of the years, I have solved similar problems more than once. And this has given me an appreciation of how my own coding style changed over time. So when I see a piece of older code, my instinct is to ask myself, how would I write this today? So imagine you are me, and you have just stumbled over this piece of old code. Now, I'm not looking for in-depth analysis here, just a gut feeling. Who likes this style of code? Don't see any hands. Who does not like this style of code? Yeah, I don't like it either, and this is why. It interleaves the core functionality with error handling, making it really hard to see what the function does at a glance. In addition, the return value is not the return value, it's just a success flag. It tells us whether the function succeeded or failed. The return value is hidden at the end of the parameter chain. We're not going to mix those two up, are we? Use exceptions and you might get something like this. Except you have to throw somewhere up the call stack and you have to catch somewhere down the call stack. And if you don't catch or if you catch the wrong type of exception, your application crashes. And also, should we use exceptions for the main errors? Not sure. Some people can't or won't use exceptions. So I guess this is not the solution for everybody. Okay, back to square one. Other ideas? We like classes, right? So why not make it an error flag class member? Now every function can just look at it, see that an error already happened, and write to it. Looks promising. Except that we just move the checks around in truth, and if we fail to check in one of the functions, we might get some funny behavior. And congratulations, we have just created our own little dependency hell. Every function now depends on this single error flag, no matter whether they had anything to do with one another before. This is called shared mutable state, and it's poison to local reasoning and thread safety. So let's take one step back and just fix the return value issue. And we can do that by combining the success flag and the return value into an optional of the return value type. There's no ambiguity anymore. If the optional is empty, that implies failure. If it has a value, we can use it. And then we throw away all our if statements and let optional do the work for us. This way, the sequence of the function is plain and clear to see. We also can't forget about the error handling anymore because optional does it for us using this end-then function here. This is a monadic operation in action. I've set myself 3 goals for this talk. First, after the talk, I'd like you to understand what functors and monads do. Not what they are, that's quite a different story. So my focus for this talk is on practical usage, not theory. Secondly, after the talk, you should be able to use the monadic operations that come with C++ easily, and that includes some initial advice about fixing compiler errors and avoiding some surprises. And finally, if you find the topic interesting, I want to give you enough leads and references so you're busy for a few days or weeks after the talk, if you choose to do so. Everything that you see here, all the code, the slides, lots of links, is behind a GitHub, and I will share the link at the end of the talk. And of course, there's going to be slideware. So the code on the slide would kind of work, but I would advise you not to use it. Use the GitHub link, or there will be Compiler Explorer links as well. And did I mention I have children? I managed to get rid of the dinosaurs. They were just too dangerous, but there might be a couple of unicorns still hiding in this presentation. Okay, we need to start with functors, because functors form the foundation before we can talk about monads. And now a question to you. Is this a functor? Let's have a little poll. Who would say, yes, this is a functor? And who would say, no, this is not a functor? Well, both would have been right, because the name functor is ambiguous, it's overloaded. And this is something I would call a function object, an object that can be used in a way like a function, but it's not the functor we're looking for. So what are we looking for? Let me start with a little story. Once upon a time, there was a little sequence of code, and it consisted only of two functions. One, to calculate the area of a circle from a radius, and the second one, to format an area nicely into a string. They were combined, so you could enter a radius and get a formatted string of the circle's area, and everything was good. But then a developer came, and she brought a vector of radii. And of course, she wanted a vector of formatted strings. No problem, they said, we'll just make a loop. And inside the loop, we will pretty much do as before. But then one of the functions said, this does not feel right. I'm sitting here together with code that knows nothing about radius, area. It has nothing to do with me. I fear we have violated the single responsibility principle. And when I asked the seer what he sees in the future, he just said, code duplication. How much better would it be if somebody could magically transform us poor functions to be able to handle vectors ourselves? Maybe we create a new function from the old one, taking the old one as an argument. So the new function would take a vector of whatever input parameter the old function accepted, and would return a vector of whatever output the old function returned. So for format area, which accepts a double and returns a string, we would now accept a vector of double and return a vector of string. Now we can combine those two new functions, and they could natively handle a vector of radii and return a vector of formatted strings. The vector aspect would only be implemented once. This is one way to use and implement a functor. But I'd like to show you a different one, which is maybe more common in C++. Let's think about a functor as a container or a magic box. Put in a vector of building materials, send in a worker, a single worker with a plan, take out a vector of houses. So how would we implement that? This time I use a class, and the class holds the value that I want to transform in the next step. As we have seen, this is not necessary for a functor, but it's often convenient. Here we pass the function that we want to use to transform the values into a member function of the class called transform. It will apply this function, which works on a single item, to all items in the vector. And then the result is a new functor, so we can immediately repeat the process. Again, the vector part is implemented only once. So you have seen two different approaches. Both are functors, and both solve our problems. But what's going on in detail? Let's start from scratch again. So we know we can have a radius, and we can transform it into an area, and we can create a string out of it. Now looking at the vector side of things, we can construct a vector from one or multiple radii. We could do the same for area and string, but that's not what we're interested in. So how do we get a vector of areas? We use functor magic to take the function that applies to a single item, and the functor will make sure it happens for the whole vector. And then we can repeat the same thing for the next step in the pipeline. And the nice thing about this, we are not bound by vector. We can just switch it out and use, for example, optional. Our functions don't need to change. Now, a little theory. Functors have to follow two rules. First, the rule of composition. Because we could, of course, combine the two functions that we have into a single function by just wrapping it. And of course, we could apply this function on our functor. And the result should be a vector of strings. And in fact, it should be exactly the same vector of strings as you would have gotten if we had followed the pipeline step by step. The second rule says that identity needs to be preserved. What does that mean? This time I use a different function, std_identity, which accepts a parameter and returns it unchanged. Sounds silly? Please play along. So, of course, it's a good function. We can pass it to our functor. And the result must be absolutely identical to the input. Again, does it sound silly? It has real implications because it means the functor cannot use any other state, internal or external, to come to the result. They are only allowed to use the function and what the function does. So in summary, a functor provides a mapping between categories such as from single values to vectors to optionals to other things. And this mapping has to preserve composition and identity. We've seen that functors can be implemented in different ways, that they don't have to be objects, that they don't have to hold a value, although in practice they often will. And we will see examples from the standard library. Now, I have used vector as an example to show what benefits a functor brings. But of course, they're not only vectors, there are other containers, there are ranges, anything iterable. And of course, we don't want to write such a functor ourselves. And we don't have to, because the standard library has std_ranges views. When we look back at the vector example, specifically on the classic implementation, the code below is the implementation using std_ranges views. How does that work? Again, we have a transformation function, a transform, and this time it has two parameters. The first one is the input value, and the second one is the function or callable that I want to apply to this input. And now I have an inner transform, and the output will become the input for the next transformation. Now, this notation with inner and outer transform is not really convenient, and it can get downright confusing when the pipelines grow longer. So the pipe operator to the rescue. This way, the pipeline looks a lot more natural, and it's, at least to me, clearer to read. How does that work? We start with our initial input. The pipe basically injects the input into the first transform function. Then we apply this transform. And the output of the first transform becomes the input of the next transform. But there's two questions here. What do we actually return here? And what type is the view? Let's answer the second question first. Because the result is not a container, it does not contain values. Think of it like a recipe, not a cake. It tells you how to get cake when you bake it, but you don't have cake yet. The views also typically do not own the data that they work on, so you have to be careful about the lifetime of the input data. And views are lazy. So what type is the output now? Something like this. and it varies by compiler. So auto is pretty much the only way to make use of it, and that has some implications. When we return a view, which we can do, we have to use auto as the return type. But this does not make it a template function. Still, we cannot separate declaration from definition, so when we use this function from multiple files, we will run into trouble. So my recommendations: mark such functions inline, don't overuse them, and try to keep the scope small where you use them so you still know about the lifetime of the data that the view is based on. Alternatively, we can return a container, and C++23 makes that really easy with stdranges too. So we convert it into a container and get a clean API, and we can again separate declaration from definition. You can use both standard library containers but also third-party library containers if they have the necessary interfaces. For example, I know that Qt works with this. What you lose is the lazy evaluation, because everything has to happen in that single line of code. All the results have to be computed and filled into that container. So to summarize, views are like a recipe, not like the cake. They typically do not own the data, so be careful about lifetimes. Auto is the way to use them, and they evaluate lazily. And there are traps. Of course there are. This is C++. So who can find a bug in this code? And there will be a microphone available if somebody wants to say something. And I will give you a hint. Okay, let me walk you through it. We have a pipeline with two transformations. And in the first transformation, we call getNearestEntry, which returns a C entry, a simple struct. In the second transformation, we just want the text member, mtext. And so we use the member. But this way we get a reference to the member, and the C entry struct that we got was just a temporary. It goes out of scope, poof, and we are standing here with a dangling reference. Now, this is nothing specific to ranges views, but with the laziness and the notation, it might be a bit harder to spot. So be careful and always use a sanitizer. You might have noticed that passing callables is a very important aspect of using functors, and that goes also for monads. When I started using this writing style, I often had difficulty finding the right ways to fit my functions into the functors, wrote complex adapters, and in some cases just threw up my hands in despair and went back to imperative coding style. I'd like to spare you some of the trouble, so I will show you some ways to feed your functors. And the easiest way is to use of free functions, and we have seen that, unless they have overloads. We will come to overloads later. Static functions of classes are pretty much the same. You just have to add the class name for qualification. Inline lambdas are a very direct way. You code what you want directly where you use it, which is mostly suitable for small functions and for functions that you don't want to reuse elsewhere. And one very nice use case is overloads. Because if you have an overloaded function, the compiler will often not be able to deduce which overload it should use. Wrap it with a lambda, and it usually works. Another typical issue is that you have a function with multiple parameters, but the functor will only provide one of them. Again, we can use a lambda. The single parameter gets passed into the lambda parameter, and the remaining parameters are in the lambda capture list. Calling a member function is also quite common. Here, the functor gives us an object instance, and we want to return the result of a specific member function. Well, I can easily do that with a lambda. The other way around, maybe the functor gives us a value that we should pass to the member function of a known object instance. Here, we pass the object instance via lambda capture and then call the member function on it. If you want to use a lambda multiple times, or just give it a name for readability, you can do that with named lambdas. And you can also use function objects that you write yourself, which work pretty similar to lambdas, but they give you a bit more flexibility. An interesting option is if you want to inject behavior from the outside. You can use std function to do that. Std function wraps any callable with a specific signature, so the template parameters are the return type and the argument types of the function. And then you can use any callable or function that matches this signature. And then we can pass this std function into our pipeline and it will do whatever it does. This way, we do not have to templatize our own code. But of course, that's also an option. We can get callables as template parameters. If we want to check if the signature is right, we can use the std invocable concept. Templates typically have better runtime performance compared to std function, but they come with additional complexities in your code. So to summarize, there's many ways to feed your functors, and I have not shown you by far all of them. Lambdas are very flexible, so they are good basis. And if you add std function for cases where you want to inject behavior, you should be good for most of your use cases. Now that we know what functors are, we can talk about monads. Because monads are basically functors plus something extra. But let's again start by looking at how a monad helps us solve a problem. Let's say we have some kind of tree-like structure. So we have a node, and the node has children. So I have a function called getChildren. It's not important how exactly that works. What is important is that we can get multiple children. So of course we get a vector of nodes. Now, we cannot repeat this process because getChildren is simply not equipped to handle a vector of inputs. So what can we do? Functors have been helpful so far, so let's see if they can save the day again. So we start with our vector of nodes and we apply the transform and we get a vector of nodes. The next transform is not going to be happy about that. So what do? We invoke monad magic and join the nested vectors or flatten them into just a vector of nodes. This way, we can continue and do the transform again and do the join again. So for our practical purposes, a monad is a functor with the ability to unwrap a level of nesting. This is a very hand-wavy definition, so don't go to theorists with that one. But I want to focus on practical examples rather than theory in this talk. What you typically cannot do is unwrap the last level of nesting, because what would you unwrap a vector of ints to? The rules for composition and identity still apply because a monad is a functor. And transform and join are often combined into a single function, which will vary by name depending on your monad. And we will see a couple of examples. But let's leave theory behind and look at examples. It has been said that the compiler is a tool that takes files as input and produces diagnostics as output. Let's ignore the fact that it might also produce something useful like object files and focus on getting and printing out the diagnostics. And for that, I have a little helper function which is able to print a single diagnostic. Then I have the compile function which takes a single file and will give me all the diagnostics for that file. And typically, we might want to compile multiple files, so I created a function called getFilesInProject that just takes a project, whatever that is in my case, and gives me a vector of files. And that would be my classic implementation for that. So we loop the projects, we get all the files in the project, then we loop those files, we get the diagnostics of a single file, we loop the diagnostics, and finally print them. Who uses such code in their code bases? Okay, about close to half, I would say. All right, how would we write this with ranges views? So we start with the project that is our input. Then we transform them into files, which gives us a vector of vector files. So we join, making it just a vector of files. This way we can compile, giving us again a vector of diagnostics. So again we join, flatten it to a vector of diagnostics. And then we can just loop those diagnostics and print them. So here are both versions for comparison. So what do you think? Which one makes the intentions of the author clearer? Do they behave differently? Well, in this case, no, because I immediately start drawing data out of them. Remember the laziness. So as written here, both will call the same functions in the same order with the same parameters. I'd like to sidestep a little here and talk about the topic of using functors and monads, and specifically ranges views safely. And pure functions are a key to that. Who knows what a pure function is? Okay, almost half the room. For all the others, I'll explain in a couple of minutes. But let's first look at a motivating example. Here we start at the bottom of the slide with a vector of numbers. And what I want is a view where all these numbers have been multiplied by 2. And we use a function to do that. The function is above. getMultipliedView takes our input, our vector, and a multiplier. Inside the function, we have a helper lambda, which handles multiplication of a single item. And it receives the number it should multiply as parameter and the multiplier via lambda capture. And then we just return a transform view, and we can use it in our calling code. So we print the output, doesn't matter how exactly, and what would we expect? So we start with 2, 4, and 6 times 2, that should be 4, 8, and 12. Wait, okay, that looks like a bug. Okay, what's going on here? So first, we pass the multiplier by value. That's fine, I guess, for a double. Then we capture it by reference, which could already be called a little fishy, but would still be okay. But then we use ranges views, and they are lazy. So the lambda will actually be called only after the function scope has already been left. And again, our multiplier is a dangling reference. This is an example with ranges views, but you have to be aware that in general, functors and monads control when your function gets called, how often your function gets called, and in which context your function gets called. So how can we avoid abuse of our functions? Mainly, I see 2 choices. We can redefine print in the documentation of the functor, if there is one, if it's accurate, if it stays accurate. Or we can try to make our own code more robust by making it purer. And that's the option I'd like to explore. So what's a pure function now? It has 2 properties. First, it will give you the same result for the same input, and it has no side effects. What does same result for same input mean? Consider a function with some inputs and an output. If you had infinite memory, could you replace it by a lookup table? And if the answer is yes, then we're good on that requirement. What does no side effects mean? It means the function does not write to outside memory, outside of its own stack frame. It does not cause any external effects such as I/O. So basically, all the function does is return a value from the tip of the green arrow. Pure functions have a lot of advantages. They're easy to reason about because you just have to look at the function, not any surrounding code, to understand what it does and how it does it. It's easy to write unit tests for them. You can use a part of this lookup table to check in the unit test whether the function does return what you expect it to do. And if it's really a pure function, it's inherently thread safe. So pure functions are useful for functors and monads, but they are useful in more general terms. Because let's say we have a complex function that interleaves logic with lots of side effects. This will be pretty hard to unit test. You have to cover a lot of branches and you will have to check for various side effects. And I like to split such functions into a pure logic function that has as much complexity as it's possible, and a simple execute function which takes the output from the logic function and applies it by picking which side effects it should trigger. And as needed, I can write a wrapper so to the outside world it still looks like a single function. But now I can test those two separately, and each of them is easier to test than both combined. The pure function, because I again can use this lookup table approach, and even the execute function is typically easier to test because I can more easily choose which side effects I want to trigger. Now let's have a little quiz. I will list some functions from the standard library, and you tell me whether you think they are pure or not. First is stdmax, calculating the maximum, in our case of 2 numbers, 2 integers, no custom comparison. Who thinks this is pure? Who thinks this is not pure? Okay, everybody's right, this is a pure function. Next is stdfill, that we can use to fill values into a container or range. Who thinks this is pure? And who thinks this is not pure? Excellent. It's not pure. We are writing to memory outside of our own stack frame. Std chrono system clock now. Who thinks this is pure? Who thinks this is not pure? I have a high quality crowd here. This is not pure because how would you replace that with a lookup table? stdsyn, calculating the sinus of a double. Who thinks this is pure? Who thinks this is not pure? Well, depending on platform, it will not be pure because it might depend on global states such as rounding modes. stdups, for calculating the absolute value of an integer. Who thinks this is pure? Who thinks this is not pure? Yes, it's almost pure, but what do we do with int min? That's undefined behavior. So can I now call it pure or not pure? I can't really say. Last one, stdAnyOf, a function that will check if a predicate holds for any item in a range or container. Who thinks this is pure? Who thinks this is not pure? Well, here we are depending on the predicate for a start, because if the predicate has side effects, so do we. But even with a pure predicate, we could argue that it uses iterators, goes to outside memory, so can we guarantee again the lookup table rule? What I wanted to show with this quiz is that purity of functions is not just a black and white thing. There's a lot of gray area in between. So on the one hand, pure functions help us write safer code. But then most functions have some kind of impurity in them. I take a very practical approach. Make your functions as pure as is reasonable for your specific use case. And going back to our example, one way to look at it is to say that this lambda is not pure because it's depending on outside memory. We can improve that by making the capture by value. I would still not really call this pure, but it's pure enough to solve our problem. In the example so far, all the functions I used did not have to communicate some kind of failure. So, of course, to keep things simple. But in real life and in production code, we typically have to handle failure in some way. And if we are not inclined to use exceptions, at least for the domain errors, then we need something else. In the following sections, I want to compare a classic value-based error returning approach to std optional and std expected. And our example is this. We have some kind of storage structure, database, doesn't matter, and it holds very different types of data, like trends, images, or tables. And looking more closely at the table, we can identify a column by index or key, and we can do the same for the row, which gives us a cell. Now we can look inside the cell and see if there's a number in there. And if there is, we can check if the number is negative. So this is what we want. We want a function that tells us whether the value inside the table cell is negative. What could possibly go wrong? Well, the key to the database might be invalid. It might be valid, but not a table. Row or column index could be out of bounds. The value might not be numeric. Finally, we have one operation that won't fail, at least for the integer that we are using. And these are the helper functions for a classical implementation. And the first one is called getElement. So we pass in a database handle and a key, and we receive an element as last parameter of the function. Because the bool return value of the function is just a success flag. It tells us true, the function succeeded, or false, it failed. I see those a lot in older code and I hate them because you cannot compose them and they will often call more constructors and destructors than necessary. But that's what we have, so let's see the rest of the functions. getTable extracts the table from an element, and again, the bool return flag tells us whether the function succeeded. getCell allows us to access a certain cell by location, so it has a second parameter here. And getNumeric cell value will give us the integer value of the cell if the type is correct. Does anybody have a flashback? We have seen this code before, so let's walk through it. This is how we call the functions. We create an element on the stack and then ask getElement nicely to fill it for us. And if getElement says, no, I can't do that, we ourselves return indicating failure. Same for the table. We create a table on the stack, ask getTable to fill it, early exit on failure. And for the cell, and for the integer value. Finally, we have our value. We can check whether it's negative, and then return indicating success. Who has code like this in their code bases? Okay, that's, I would say, about more than half maybe. So how would we write this in a more declarative monadic fashion? First, we change the interfaces of our helper functions. Instead of returning bool, we combine the return value and the actual result into an optional of the result type. Now, when a function now fails, it simply returns an empty optional, and that indicates failure to us. If it succeeds, it returns the element as before, in this case, wrapped in an optional. And we do the same for getTable, getCell, and getNumeric cell value. Now, for the sake of completeness, I have also added a check to see if a number is negative. Of course, that's not necessary. Could be an inline lambda. But the interesting part here is that we return bool. We do not return optional of bool. Why? because this function itself cannot fail. And then let's see how the pipeline works. We start our chain by calling getElement. And getElement will return an optional of cElement. Now, optional allows us to call the next step of our pipeline conditionally, that is, only if the optional contains a value at that point. And that's called end-then. We pass the function that we want to use in the next stage of the pipeline into the end-then. If the optional is empty, we will still get an optional of the correct type as a result, but it will just be empty. Since we are working with values that may be there, this is also called the maybe monad. So let's assume that getElement worked fine and also getTable gave us a good table, so we now have an optional with a table inside. Quiz time. I don't see any join here. Is there any unwrapping going on? Why do I call this a monad? Does anybody have an idea? There's microphone, please.
Because what and then is doing is calling transform and then join inside it.
Okay, you sound like you already knew it. Okay, yeah, indeed. So what happens is that we call getElement and it returns an optional of cElement. But getTable does not get an optional of element, it just gets an element. So we have successfully unwrapped one level of nesting, like a good monad should. Now, how would we implement join in this case? Because let's say we have an optional of int, and we want to just unwrap it to optional of int. And optional does not have a function called join that we could use directly. Any suggestions? I will give you a hint. Okay, I will just uncover it. Because we can use the identity function to short circuit the transform part of the end-then, like you said, and then is join plus transform. And since transform with identity needs to come to the same result as we had as input, we basically only get join that way. I'm not sure I would like to have this in production code, but it's good to illustrate the guarantees that monads give you. Okay, back to our code. So we pass the table to our next function called getCell. This one needs a second parameter, the location. So here we just pass it by lambda capture. And let's assume we gave bad location. Our optional is now empty. Because of that, the next end-then in sequence will bypass the function get numeric cell value because the optional is empty. The type of the optional will still be changed to optional of int, but it will just be as empty as the input was. Finally, is negative does not return an optional of int, so we don't use end-then here. Instead, we use transform, just like in the ranges example. We want to transform an integer value to a bool and use the function. Still, it will only be called if the optional has a value. So what can you do with optional? Here are the basic operations. We can check if it holds a value, and if it does, we can access the value. If you try to get the value from an empty optional, it will throw an exception. We can simplify it by moving the assignment into the if statement, and that way we both assign and check whether the optional holds a value, because the operator bool for optional tells me whether it holds a value. If I only care about getting a fallback value in case that the optional is empty, I can even further simplify it and use the function value or. It will give me the value inside the optional if it has one, Otherwise, it will give me the fallback value that I pass a second parameter. And here again, both versions of the code, classic on top, monadic on bottom. Let's have a little poll. Who prefers the classic version of code? And who prefers the monadic version of code? I would say that's a clear majority. Now, we handle our errors, there's nothing bad going on, but what if we want to do some logging? We can use a sibling of and then called or else. It works exactly in reverse. It will only call the function that we pass as the single argument if the optional is empty. Since emptiness is our indication of failure, we can use that to trigger a log function. Now, why is it a template function? Because it needs to return an optional of the correct type. Since it does not get an input parameter, it cannot deduce this type. So we have to tell it some way what type we want to have. Of course, if you know the type upfront, you don't have to templatize your function. Now, we have a little problem here, because let's say an error happens in getCell. We can catch it fine with the log function, so we catch the fact that we have an error, but we have no error context. We have an empty optional and that's it. We don't know where the error happened or what exactly happened. There must be a better way to do this. And this is where std_expected comes into play. Std_expected is a new type with C++23, and it's very similar to optional. So instead of optional, we change our functions to return std_expected. Now, expected has two template arguments. The first one is the value, just like for optional. The second one is error information. When a function now fails, it does not return empty, it returns unexpected. And in the unexpected, I construct an error type. And in my case, I use the custom type called CR, which accepts an error message as a parameter to the constructor. It can also, in C++23, capture the call stack so that you know exactly where the error happened. And if you're interested in this feature, please look up the stack trace library. There will also be a link, a reference behind my link. If everything's okay, we just return a value as before, wrapped in an expected this time. The pipeline looks exactly the same and then uses the same logic. So if the expected holds a value and then will call the function. Now, if a function fails, it will now write error information into the expected. And the next, and then will then bypass the function. We retain the error information, and we can carry it all the way to the log function. We can capture it with or else there. The log function will now receive the error type as a parameter. And now, for example, if getCell had an error, it writes the error message, we capture the call stack, and we carry all that information down to the log function. And now we can do some really useful tracing. Now the log function also has to return an expected, and we can choose, do we just pass through the expected that we got? Maybe I could amend the error information, give it more context. I could also choose to return a valid fallback value, but I would probably not do that from a log function. That might be confusing. The usage is very similar to optional. So we can check if it holds a value, we can access the value, and now we can alternatively access the error. An expected always holds either a value or an error. Again, we can move the assignment directly into the if and check and assign in one step. Value or exists as well for expected. So we can also fall back to a default value if we want to. Error or exists as well, but that's more for specific use cases. Now, if you have a fragmented code base or you use libraries that use expected, you might end up with different error types. So let's say we have a function that gives us an expected with C error, but what we really want is a my error, different error type. So what we do is we write a conversion function which accepts a C error and returns a my error. And then we call transform error. And if the expected holds a value at that stage, no values will change, only the type will change. If it holds an error information, then this error will be converted. We have seen how you can use optional and expected to check if all functions in a pipeline succeed. But sometimes you need the exact opposite. You want to call a sequence of functions and take the first result that makes sense. And that's easy to do with optional. So, for example, we want to start an application and find out what UI language we should use. And we have given the user 3 ways to define the UI language. First, via command line, via registry or a similar system, or environment variable. And finally, we have a fallback, so in case the user chooses nothing, we know a fallback language that we want to use. And this would be the pipeline using std_optional. In this pipeline, the first function that returns a value wins. So let's assume that get language from command line failed and we have an empty optional. Because of that, or else will call the next function. And let's say this function succeeds, we now have an optional with a language. And because of that, the next or else will bypass get language from environment, and the optional will be unchanged. If we don't have a value at that point, if the optional would be still empty, value or would guarantee that it's filled with the default value. Quiz time. Maybe you noticed that I put monad in quotes in this section. Does anybody have an idea why? It's a tough question if you're new to this. Let's consider what we learned about functors and monads. So the functor dimension is transform. We can go from optional of A to optional of B to optional of C. That's what functors give us. The monadic dimension is the ability to unwrap. So we can go from optional of A to just optional of A. And as we have seen, std_optional combines those 2 dimensions and creates the end-then functions, which kind of goes diagonal on this table. What does this have to do with or else? Nothing at all. Because the first function in our pipeline defines what value we expect, what value type we expect in our optional. There's no movement across this table. There's no transform, there's no join. This is not a monad. I would maybe call it a monadic style operation, but it's still useful, so I included it in the talk. One of the first obstacles you'll likely encounter when using monadic operations are compiler errors. In my experience, I spend a little more time fixing compiler errors, but less time fixing runtime errors, which I think is a nice trade-off. Still, I don't exactly love fixing compiler errors, so I wrote up some heuristics and a checklist to fix the most common ones quickly. So we have a little example, and it does not compile, and this is what the compiler tells us. That dreaded wall of text, in this case, courtesy of MSVC, Clang and GCC are not that much better. So what I learned is that it makes sense to focus mostly on the beginning and on the end of the error message. Here, at the beginning, I will find that something like matching call operator could not be found, and both Clang and GCC will tell me something similar. And at the end, I found out that some template argument could not be deduced. Okay, let's look at the checklist. So we start by asking the question, in which step of the pipeline did my error actually happen? And if you have trouble figuring that out, split up your pipeline with intermediates, and that should help you pinpoint exactly at what step the error happens. Then, when you know in which step it happens, ask yourself, does the function that I use here use overloads? Is it overloaded? And if that's the case, use the wrapper lambda trick. And this, by the way, is the error that we got in our example. Of course, you could also choose to change your functions so that they are no longer overloading, but that should probably be a design choice and not the result of a compiler error. Does my function accept the correct type? And if you're using lambdas, you might want to replace auto with the specific type that you're expecting, if possible. And very similarly, does my function return the expected type? And again, if I use lambdas, try to make the type explicit. Specific for std ranges views, I sometimes miscount the number of joins I need, so a function gets thing when it expects vector thing or vice versa. And do you use views as const or const reference, maybe in a template function? Don't do that, you will get strange compiler errors. Views are semantically references, but they are meant to be used by value and non-const. For optional and expected, I sometimes mix up and, then, and transform in complex pipelines. So a function returns thing, but I expect it to return optional of thing, or vice versa. So going through this list, this checklist, which you, by the way, you can also download behind the link, this should help you deal with the most common compiler errors at the beginning quickly and efficiently. Let's now leave the comfortable path of monads provided with the language and try something new. Let's write our own monad. We have studied optional in detail, and there's something pretty similar in the language, a pointer, because a pointer can be null or it can point to something. So why not write the pointer monad? I will reuse the example from optional, so the goal is still to check if the value inside a table cell is negative. And when I take the helper functions of the classic version, I change them to return pointers, or in case of the last function, get numeric cell value an optional, because it didn't make much sense to return a pointer to an integer. Now, you might notice that this looks pretty similar to the optional style, returning my result instead of giving a success flag. And when I look at the classic implementation of the pipeline, I change it a little bit to work with the pointers. And by moving the initialization of the pointers into the if statements, I immediately can check if the pointers are valid. I'm not sure if I'm a fan of this code, but we'll see something better soon. And the whole function now returns an optional of bool. It also didn't make sense to return a pointer to bool. And this is how I would like my code to look. And that's how I do it with the monadic wrapper. So this is the sequence. We call our first function, which returns a pointer, and immediately wrap it into a monadic wrapper, in my case called cptr. cptr gives me a function called and then, which is behaves the same way as optionals does. It will call the next function only if the pointer is valid. And it will pass a reference to this function, not a pointer. So then we expect getTablePTR to also return a pointer. It can be valid, it can be null pointer, both work. The same goes for getting the cell and for getting the numeric value of the cell. Now the transform here is interesting because cptr does not have a transform function. How does that work? GetNumeric cell value returned an optional of int. So I can seamlessly transition from pointer to optional monad and get my final result as an optional of bool. So how is that implemented? We create a class called cptr that should act in most ways like a pointer. Since we want it to support multiple types of pointers, we make it a template class. But we only want to accept pointer types, so I constrain the template argument to be a pointer type using C++20 concepts. The default constructor will create a null pointer cptr object, while a custom constructor can already take a pointer and we can directly initialize from there. Then there are some helper functions which allow me to produce some pointer-like behavior, like an arrow operator. This is certainly not the complete list. More convenience could be added. But it's a good basic set. And then we come to the fun part, the monadic wrapper. To be consistent with optional, I call it and then. So we will pass a callable via template parameter. The return type, we don't know it yet because we have to deduce it from what the callable returns. So for now, I use auto. In the implementation of the function, or before the implementation of the function, I first have to specify my template arguments. And as a reminder, tptr is the class template argument, which is the type of pointer my class currently holds. And tcall is the callable or function that I want to pass, which is the function template argument. Inside the function, I prepare two helper types. The first one is tref. That's the equivalent reference type to my pointer type, tptr, because we will want to pass a reference, not a pointer. And the second one is tret, the return type of my callable that I got passed. And we can get that using std_invoke result t. And as you see, we will want to pass the reference as a parameter, not the pointer. And then I have two branches. In the first branch, I handle functions which themselves return pointers. So we check if our own pointer that we have currently is valid. And if it is, we can call the callable. We forward the callable and the dereferenced pointer. We wrap the result directly into another instance of cptr. And this way the pipeline can immediately call the next and then in sequence. If my own pointer is null, I just return a null pointer version of cptr, but with the correct type. The second branch handles functions which thus do not return pointers. And for now, I only support functions which return optionals. And I use this code here to check whether the result is an optional to something. It doesn't matter what's inside the optional, it has to be wrapped in an optional. Then, again, I invoke the function if the pointer is valid. But this time, I just return the result without wrapping it. Again, if our own pointer is not valid, I return an empty optional of the correct type. Here I highlighted the differences between the two branches. Wrap pointers into CPTR, but leave non-pointers as they are. Of course, we could also consider other cases, but for now, I just added a static assert at the end so that I will get a good compiler error message if somebody passes me a funny function that does not match my expectations. And here, once again, the usage in the pipeline. And of course, there's lots we could add. We could add transform, we could support functions returning CPTR, many more things. But I hope I could illustrate what it means to write a simple monad. Because writing monads is actually not magic, although they seem to do magic stuff sometimes. It's actually not even that much code, but you have to use templates, so brush up your metaprogramming skills. Monadic operations are useful on their own, but you can do more. You can combine them. In this section, I'd like to show you two things. First, two more monads that we have not seen before, and then how you can combine them. I won't go into too much detail this late in the talk, so I will show it mostly conceptually. I still hope it will be useful, and if you find use cases for these monads, you will have the code and references to look them up further. So again, we have a pipeline and it's really slow, like really slow. Okay, I guess I don't want to block on this one. So what can we do? The continuation monad allows me to specify a pipeline and start it non-blocking. The result gets wrapped in a future, which is available immediately or almost immediately, and it will start computing the value inside in a separate thread. As soon as the first future is done, it will, via continuation, trigger computation of the second one. Again, monad magic comes into play because the function gets its input value unwrapped, so it does not have to handle future of something, it just gets something. This way, we can reuse the functions we already have. Only requirement, they have to be thread safe. Since our functions are pure, that's not a problem. Now, C++23 does not have anything like a continuation monad. There's something cooking, but I wanted to show you something you can try out right now. And the best and most production-ready library implementation that I know about is Qt Concurrent, a part of the Qt framework. You can use it starting C++17. Here I start a pipeline by calling Qt Concurrent run. And it takes two parameters. First, a function that should be called in a different thread, and then an initial value for that function. Then I can attach a continuation using the then function. It works similar to end-then. So here I pass the next function that should be computed after the first one is done. And my result, what I hold now, is a future to the final result. And I can do many things with that. I can query for status, I can cancel it, I could attach a notification so I'm woken up when the future is ready. Here I do the simple thing and I just block until it's done. It's an example after all. And then I have my result and I can print it. Now, how would I add tracing to such a pipeline, or in fact to many such pipelines running in parallel? And of course, we don't want to synchronize them with the global mutex or anything like that. How could I do that? Well, there's a second monad, as I said, the writer monad. It makes tracing part of the call chain. How does that work? We have a wrapper again, like for many functors and monads. And this wrapper holds our value, so it's a template class and it can hold any type, similar to optional. Now, when I call and then, I implemented it such that we can pass a second parameter to the and then, and that would be the trace information. So as you see below, the wrapper now holds the new value and the trace information that I got from and then. And I can repeat the step and accumulate the trace information over the whole pipeline. Finally, I can read both the value, the result, and all the trace information that has been collected. I can loop through it and print it, or whatever I want to do with it. Now, this does not sound super useful. There's a better way. If you are able to change the interfaces of your functions or wrap them into something, then they can return both the result and the trace information. That way you can trace input parameters, intermediate values, whatever else you like. And the pipeline also got simpler because the and then now only takes the function and the function itself will provide the trace information. You can combine both ways if you like, so simple version for simple functions, complex version for complex functions. And this is how we can now combine the continuation and the writer monad. This needs a little clue. So Qt concurrent run expects a function and an initial value, and the simplest way to make it work was to write a simple make writer function, which does nothing except constructing a cWriter object and passing the initial value into its constructor. That's it. So we now have a cWriter object in our continuation monad. This means that then needs to the function called by then needs to understand the cWriter interface. It gets a cWriter of something and it needs to return a cWriter of something. Our own functions cannot handle that. So I wrote a little wrapper which accepts our normal function and returns a new function with the write API. Again, this wrapper function will call our original function and additionally handle the tracing aspect. The same works for the last stage. And we end up with a cWriter of string, the string being our formatted area, our result. And again, I can loop through the trace information, print it or do whatever else I like. So on the one hand, we have the continuation monad, which makes it easy to offload tasks into threads. On the other side, I have the writer monad, which allows me to implement a log-free tracing. When I combine them, I can get independent per pipeline and log-free tracing, even concurrently. Of course, you can also combine the writer with the other monads that we've seen, expected, optional, ranges, if you want to know exactly what's going on inside your pipeline. So where does everything we have heard and seen leave us? What does it mean to you in practice? Well, I have three main takeaways. And how strongly they apply to you will, of course, depend on your prior experience, what you code, how you code, with whom you code, for whom you code. So please pick whatever you feel is appropriate for you. My first takeaway is that monadic operations, but more generally functors and monads, are really useful concepts to know about. We have seen how functor magic helps us lift out common repetitive code, separating the what I do from how and where I apply it. So I can have a function that works on a single value and easily applied on optional, vector, future, whatever. And all without needing to change the function itself. Then we've seen how Monad Magic does the unwrapping, giving us the ability to write pipelines that we could not have written with functors alone. I hope this talk has given you a taste of how useful functors and monads can be. And this is actually just the start. If you follow some of the references behind the link I'll share in a couple of minutes, you will find out how much further you can take functors and monads. My second takeaway is that pure functions are good for your code. And that applies beyond use with functors and monads. Because they make it easier to reason about your functions, they make it easier to test your functions. So even if you should decide that all this functional stuff is not for you, please take this one to heart. And the final takeaway is that monadic operations available in C++23 are immediately useful in some common concrete use cases. And you don't need really deep understanding of functors and monads to make use of them. Please try them out. See if they fit your use cases. Just a word of caution. Don't rip out existing, verified, tested pipelines because Robert said so. I did not. Do a dry run. Test them. See if the performance and memory characteristics work for you, if that matters. And then apply the patterns to new pipelines or to pipelines that you have to rewrite anyway for other reasons. And let's recap what patterns we have seen. We have seen the ranges view monad, which allows us to build a pipeline where each input creates n outputs. We've seen optionals maybe monad, if we want to build a pipeline where some or all of the functions might fail to produce a useful result. Alternatively, set expected, if we want to provide useful error information in case of failure. And optionals default monad to grab the first useful result from a sequence of function calls. These will help you write safe and readable code. The monadic operations of C++23.